Welcome to this year's virtual Soapbox Science Milton Keynes event. I'm Barbara Kunz from the Open University and I will be moderating this afternoon's session. Soapbox Science has been created as an outreach platform to bring science to the streets and the general public, as well as to promote women in STEM and highlight the fantastic research they are doing. We're very excited to have the first 6 of our 12 amazing scientists speaking today and telling you about the research they are doing. The remaining 6 speakers will be talking this Saturday, the 7th of November, again at 2 p.m. on the same platforms as today. So make sure to come along for that session as well if you can, or watch the recording afterwards. The format of today's session will be 5 minutes for each speaker to introduce themselves and talk about the research they are doing. Then we will have 5 minutes of questions. So if you have any questions for the speakers regarding their work or themselves as a scientist, please make sure to type your questions into the chat or comments and we will pick them up during the Q&A. Our first speaker today is Dr. Natalia Falagan. She's a plant scientist at Cranfield University.
Good afternoon, everybody. As Barbara said, I'm Natalia Falagan. I work at Cranfield University, and today I want to make you think about some things. First, let's start with your knowledge about food production. Have you ever thought how a bag of spinach, like for example this one, gets to your house? Well, there is a farmer somewhere in a field or a glass house using land resources, water, maybe fertilizers to grow really high quality fruit and vegetables that you probably eat every now and then at least. So this farmer can be near your house or even in another continent. You can check where your food has been grown in their label. So for example, the spinach bag is grown in the UK, so maybe it's quite close to you. But for example, this bag of tarragon, was grown in Morocco, which is quite far away. So once they are fully grown, for example, this spinach, they are gonna be harvested either manually or with machinery and then put in boxes that then goes into lorries or even planes to get to pack houses where they can be put in bags like the one I've shown you, or trays or pallets, and then go again by lorry to the supermarket. And that's the point in the supply chain that you probably are more familiar with, because we can see all these amazing fruit and vegetables displayed in refrigerated or non-refrigerated areas where you can take them, buy them, and take them to your house. This is a very, very general overview of the supply chain. It is actually much more complex. And right now, we are facing a lot of challenges that make really difficult for the supply chain, farmers, etc., to feed this world growing population. So it is calculated that more or less by the end of this century, people living in urban environments are going to reach as much as 92%. So let's think about it. Why don't we bring some of these food growing activities to cities and then we all help traditional farming? At Cranfield, we are working in a project called Rural Revolution together with Lancaster University and University of Liverpool. We've created this term rural because it's the merge between 2 words, rural and urban. And what we want is to represent this bringing food growing to our cities. And it has a lot of benefits. For example, it can help our diets because it increases the availability of fresh fruit and vegetables. Right now, we have studies highlighting that we need to double our fresh fruit and vegetable consumption to improve our health. It can also promote to support our healthy behaviors. So what do I mean with that? Our current environment in cities does not really help us choose a healthy diet. And this is because we are disconnected from fruit production. We, like citizens, we don't really normally think the effort and resources that are involved growing, for example, tomatoes. If we increase our green space exposure, if we are surrounded by green area, we will improve our dietary choices, for example. And not any green area, but specifically urban agriculture is what it contributes to this benefit. And also growing food that is really satisfying, being outdoors, it really helps our well-being, and it also reduces our level of stress. That's kind of interesting. So think about that while we also think of other benefits. For example, having more green areas will help reduce air pollution and also noise, and increases biodiversity in cities. And then focusing on the food system, having urban agriculture can increase our sustainability and resilience. Right now, urban agriculture around the world can produce around 10% of the global fruit and vegetable that we eat. That can look like a very small number, but it's actually 180 million tons produced every year by urban agriculture. So if you think about it, our current global food systems, as it stands, is shaped by multinational companies with long distance supply chains. It is quite fragile. So things like COVID, for example, this global pandemic that we are living, it really affects it. So we have been all seeing, going to a supermarket and seeing that there are shelves that are empty. We have also been self-isolating, some of us, and then you cannot really go to a supermarket. But if we have in our garden a little bit of food and that we can grow, that local sufficiency in food production can really help this resilience and this sustainability. So there are a lot of ways you can get involved: vertical farming, more traditional agriculture like allotment and community gardens. So which one are you going to choose to join the urban revolution? Thank you.
Thank you, Natalia, for this great talk. And I'm now going to hand over to Emma to ask you some questions.
Okay, so the first question that we have is, do you have any recommendations for people who want to start growing their own food? What would be a good thing to start off with?
You need to think about several things. If you want to start like the first time, maybe I would recommend to start in the summer, because with this summer weather is a little bit easier. But if you want to start now or anytime, I would recommend maybe leafy greens like lettuces, for example, because they grow quite fast. You can do it several times in the year. So I would start with that and then move into maybe tomatoes, for example. And the important thing is that you don't give up. If it doesn't work the first time, don't worry. It's a learning process, so just keep on doing it.
Oh, thank you. So what about people who don't have their own garden? Where could they grow their food?
Yeah, that's something that can happen. So there are like a lot of options. For example, you can join a community garden, and they not only can allow you to have like your own space, but also you can share tips, and they can teach you the way they grow, and you can share also what you've produced. You can also have an allotment. And if those options are not available for you, why don't start maybe in your windowsill with some herbs, for example? Yes, to start with that, and that's easy, is handy, and everybody has like a window shell to put some, I don't know, basil, for example.
Okay, thank you. So we've had a question in from Luca on Facebook asking, are there any mental health benefits of growing your own veg?
Yes, we are actually working right now in a citizen science project in Bedfordshire. So we've got together with 60 amazing participants who have been growing lettuces, and we've been monitoring the benefits. And in situations like lockdown, for example, they've told us that being outside in their gardens or in the window shell, like having some herbs and lettuces, it really helped them to get up every morning, to have an activity, and also seeing those results and actually being able to, for example, make a salad with them. So yeah, absolutely. One of the main benefits of urban agriculture.
Okay, and so at the end of your video, this is a question from me. I saw that you were standing in front of a building with pink lights, and I just wondered what that building was and why the lights are pink.
Yeah, so that's the amazing glass house that we have at Cranfield University. So there are, I think it's unique in the world. We have inside a lot of cameras to monitor like the growing of plants, and we can mimic different conditions, even tropical conditions here in the UK in the winter. And those lights is basically to mimic the circadian cycles of the growing of plants. So right now we have very short days, and if we have those lights on, then we can trick the plants into thinking that it's sunny.
Okay, thank you. So we've got a question from YouTube here. Can I grow enough to sustain myself and my family?
You can grow enough to sustain yourself and your family in terms of fruit and vegetables. So yes, and you will notice that you will have years that, for example, you plant cucumbers and you have an amazing production of cucumbers, and then you can share with your neighbor, and then your neighbor can also give you maybe some tomatoes, because if you grow enough, if you like master the growing activity, then you will have amazing yield. So yes, I mean, if you eat meat, if you eat fish, obviously not. But in terms of fruit and vegetables, having your own growing activity is really, really good.
Okay. Okay. So it would really make a difference for us to grow our own food. We had another question in from YouTube here. So to what extent are veggies grown at home more or less nutritious than farm produced?
That's a really good question. And we are actually wondering the same thing. And we have a project called Lockdown Lettuce in Bedfordshire. That is the one I was talking before. And those lettuces that our participants have grown, we've taken them to the lab, and we are comparing their nutritional content. We are comparing that with a normal lettuce. So we are actually wondering the same thing. And we are checking that right now. And as soon as we have the results, I hope I can get them to you all, so we can actually check. But it's looking good so far.
Okay, thank you.
That sounds great. And I'm really looking forward to see that. And so make sure that you check out what Natalia's results will be. And maybe you can post something about that on our homepage at some point in the future, once you have them. And if there have been any questions that haven't been answered, then we will try to make sure that Natalia will have the time to answer them and post them below the video of the live stream, as well as on our homepage. And with this, I'd like to move on to our second speaker, Julia Villa. She's a global health PhD researcher at University College of London. And she's going to talk to us about her work.
Hello everyone, and thank you for joining. My name is Julia, and I will talk to you today about the dangers of poo germs. Every day there's more people in this world, and there is at least one thing that we all have in common. We all poo. Traditionally, the smelly issue of managing poo waste has made it a very unpopular topic. But why is it important to manage it safely? And what are the dangers of poo? Well, poo often contains many sorts of germs that transmit infectious disease, such as diarrheas. And diarrheas in children may not be a big concern here in the UK, but they're actually still the second top cause of death among children worldwide. In addition, constantly having diarrhea infections damages the gut, and it makes it harder for children to absorb the nutrients from food. So infections of the gut also have a direct impact on child malnutrition, which is a persistent challenge for global health. In my house in London, I never worried much about the poo germs around me. I poo and flush, and it is carried away by long pipes to a treatment plant. And I turn on the tap, and clean drinkable water appears on demand. But this is not like this everywhere else. Last year, I spent a few months living in a remote rural area of India called Banswara. And in the rural villages of Banswara, there isn't a sanitation system with flushing toilets. So often people poo out in the open fields. In these rural farming environments, families also live with domestic animals, such as chickens and cows, and they also poo and contaminate the households. For example, here in my background, you can see a typical household in one of the rural tribal villages in Banswara. You can see the cows here that are kept close by the house, and here you can see the cow poo that is being used here to pave the floor. And also you can see the babies that are playing around the household courtyards. So what happens is that babies in these settings often end up being constantly exposed to poo germs that are spread around their households and courtyards. And they are exposed to poo germs in several different ways. For example, germs that are laying on the ground can be picked up when babies are crawling and playing and putting their soiled hands in their mouths. Or they can also be passed on when hands aren't washed and they come into contact with food that babies then eat, or maybe with toys that they're playing with. They can also get infections from drinking contaminated water. So my research is trying to understand all the factors that are contributing to babies being exposed to poo germs in these environments and identify the infection transmission pathways that cause the most diarrheal infections in babies so that efficient public health strategies can be designed. For example, what we found is that in these villages, the soil in the courtyards was so highly contaminated with poo germs that children had a higher risk of getting diarrhea infections from crawling and playing and putting their soiled hands in their mouth than from drinking contaminated water. So you may think that solutions for these problems exist. More hand washing, using toilets, or separating the animals and improving the child play spaces. But it turns out that improving the hygiene levels in these environments is not so easy. Not having running water or toilets at home or floors that can be swept and mopped makes it really difficult to keep a clean and hygienic environment. And even then, changing hygiene habits is not an easy task. For example, with the COVID-19 pandemic, we have seen how difficult it is for people to wash their hands more often. Access to safe water, sanitation, and hygiene is a fundamental human right. And the pandemic has only made this even more clear. Yet, more than 1 in 3 people in this world still lacks access to these basic services. We need more attention and political will to improve these basic infrastructures and design effective strategies that improve hygiene habits. We need a collective effort to start a hygiene revolution and achieve a safe and clean environment for all children to develop. Thank you all for listening, and please do ask away.
Thank you very much, Julia, for this interesting talk and a very important issue. Are there any questions for Julia?
So the first question we have here is, you said that there's no running water in these households. So how do people in these villages access their water?
So it does look quite different from my house in London, and water is accessed through tube wells. So tube wells are wells that connect to groundwater aquifers, and they are manually pumped to access water. And there are some issues with these water access points. Some of them go dry during the dry season, and during the monsoon season, when there's a lot of rain, they often get contaminated from all the water that is washed and washes away all the germs on the surface. And they also sometimes are quite far away from households. So people have to take time to go and collect the water, and they often store it in their households. And during storing the water, there's also many more chances for water to get contaminated. So there are a lot of gaps that can happen in accessing water that pose higher risk of infection through contaminated water.
Okay, and has COVID affected these communities in any way? It's another question that's come in.
Well, actually, conveniently enough, these communities are quite isolated. So they have very minimal contact with maybe larger populations and bigger cities. So actually that protects them maybe from potential contacts, COVID contacts. But another interesting thing with COVID and these communities is that they are much younger. So it has been seen in the whole of India, actually, that COVID is having much lower mortality rates. In these communities in Banswara, the life expectancy is around 65. And if we think of it, in the UK, for example, I think it's like 20% of the population that is over 65. So obviously, yeah, like the people at risk is much fewer.
That's interesting. So we've had a question in from Facebook here. So if you could give only one main piece of advice to these villagers to start improving their hygiene, what would it be?
This is an interesting question because there's been a lot of focus on hand washing, but I'm looking specifically at risk for babies. And the risks for babies are quite different from those of adults. If you think of it, adults will never be putting soil in their mouths from crawling on the floor. So if I had to give one piece of advice to prevent infections for babies specifically, it would be improving their play spaces where they play. So maybe providing plastic mats to put them on top of them so that they are not eating the soil, or providing maybe play pens. There's some research around that to see whether this is a useful advice or not.
Okay, thank you. So another question just coming from our YouTube view. So how easy is it to get people in these communities to change their behaviour? And that's coming from Stacey, so thank you.
Well, I think changing hygiene behaviors is difficult for everyone. If we've learned something, is that behaviors are very much ingrained in our routine, and they are often shaped by our emotions and motivators. So changing behaviors is hard in any case. But in these communities in particular, we can see that the infrastructure and the built environment is really not inducive and helpful to change behaviors either, because what is the motivation for cleaning the floor if the floor is made of dirt and gets dirty all the time? So I think the setting influences behaviors a lot, and there are many needs to improve the infrastructure and change behaviors.
Okay, we have another question from YouTube here. So can these communities treat their water? And that's come from Tolu.
Yes, they can. They actually, an easy way to treat water is boiling it. But there isn't, it is time consuming, and there isn't that much awareness of the risks of contaminated water. So it's not common. And actually, one technique that is commonly used in these communities to treat water is filtering it through cloths, so that if the water is mixed with soil, they will get rid of soil through filtering it. But obviously, this does not make the water microbiologically safe. And it is a challenge to make these communities aware of safe water treatment techniques as well.
Okay, so thank you. We've got another really interesting question from Carol. Do you take gender into consideration when you're training in these communities?
Gender is considered a lot when dealing with hygiene issues. And there's a lot of research, for example, ongoing menstrual hygiene, which is a topic that's very gender specific and has actually been quite overlooked until very recently. But in my particular field of research that is dealing with babies, maybe the gender perspective doesn't apply so much, although it still has an impact because of the burden on women and mothers specifically that have caretaking habits and practices. So women are mostly the ones responsible for collecting water and feeding children and caring for children. So it's always needed to have this gender perspective as well, I guess.
Okay. Another one here.
Sorry.
I
think
very interesting.
We have to keep a bit in time, and it's a very interesting topic. And I hope that that Julia, you will take the time to answer those questions afterwards, because I think it is a really crucial topic. And we will now move on to our next speaker, Dr. Sevi Filippido from the Open University. She's a microbial ecologist.
Thank you, Barbara. I'm a microbial ecologist interested in astrobiology. So what we're going to discuss today is going to be whether there is life in the universe. And especially on Mars, this is the research I focus on recently. So you must know, of course, that we have sent several missions to Mars. You must have also seen pictures of those robots that we very often call rovers, and they might have all sorts of names. So our missions to Mars have shown that actually Mars, in the past, a few billion years ago, was very similar to what Earth looks like today. So what we do to understand whether life existed on Mars, or if it still exists, one of the goals is to go there, either us or one of the rovers we send, and look for it. This has not yet been possible because of different restrictions, but we still want to understand whether Mars or any other planet is what we call habitable, if life can be found there. So what we actually do is that we look for it here on Earth. The environments we investigate here on Earth, we call them analog environments because they bear similarities to the other planets. And these environments on Earth, we call them extreme very often because they have these extreme conditions. One of those environments that I will use today as an example are deserts. And I use it as an example because last January, I visited the Kalahari Desert to collect samples in order to investigate how life adapts in those environments. So the samples we collect, they look something like that. They are long cores that we collect from the desert. And then we cut them open, and the sediments we collect, they look like slices of cake. Well, not much as lemon cake, to be fair. They mostly look like Rocky Road, but I ate that piece before. So in those sediments, we suspect there is life, and this life is microbial. So we do not see it with the naked eye, but we know it is there. This microbial life develops extreme survival strategies. These survival strategies are incredible, and they make this life withstand high UV radiation, but sometimes also cosmic radiation, X-rays and gamma radiation. They can survive very high temperatures and very low temperatures, far beyond what us as humans can tolerate. And they also develop community living, and one microbe helps the other to withstand the extremity of, for example, the desert. So these survival strategies, we suspect that microbes, if they exist on habitable planets, they should also deploy them. So my work is to go in analog sites, investigate survivability, investigate all the different and wonderful strategies microbes have, understand their community living, and then go and look for this community living in other planets. What I very much love saying is that our quest for life in the universe has started here on Earth, but it also helps us understand the origin of life on Earth and the origin of our existence on this planet.
Thank you very much, Sevi. That was very interesting. Thank you for taking the time to talk about your research. Let's see if there are any questions.
Okay, so the first question that I have here is, do you think that humans will be living on Mars in our lifetimes?
That's a great question. This is, it maybe pops up in every other meeting we have. So I want to say that this is yet another very important field of science. There are scientists working on that. They investigate that to understand whether humans might be able at a point to live on Mars. We do not have a solid answer for that yet. Science is always optimistic, but there is something else I need to mention here, that it's not only the scientific part that is important to discuss about colonization of other planets, Mars, for example, but also the ethics behind it. Are we allowed ethically to colonize another planet, exploit it, and if we want to exploit it, in which ways?
Interesting. So we've got a question here from YouTube. What's the most extreme environment you've ever found a microbe in?
So there are certain environments on Earth, as I said before, that they might be exposed to high radiation and some others to high temperature or very low temperature. But there are certain environments on Earth that we call poly-extreme environments because multiple stressors are present. These environments I have visited are, I think, volcanic environments where the temperature is extremely high, but also it is very acidic. I believe most of you must be familiar with sulfuric acid and how dangerous this can be. So sulfuric acid is present in volcanic environments, so it makes it even harsher. It's not only temperature life has to cope with, but also sulfuric acid. The most extreme environments, very interestingly, on Earth are hydrothermal vents that are found in the oceans, that they have both of these conditions, plus very high pressure. And this is very interesting because it is believed that life on Earth actually started in those hydrothermal vents.
Okay, thank you. So another question we've got here from Facebook this time. How different is the soil composition in our deserts to that of the planets?
So when we study an analog site, we investigate different things. Sometimes, yes, the soil composition can be very different, and other environmental conditions might be very similar, and we focus on that because we might find similarities there for life adapting. But there are actually certain environments on Earth where certain rocks that they bear high similarities to the Martian rocks. Whether these can be studied as analogs for biology, it's questionable, depending on the other context, whether they can be, for example, found in other extreme conditions as well. But from a geological point of view, they are very interesting because they're highly similar.
Okay, so I've got another question here from YouTube. You're getting lots of questions. So if we establish the possibility of life on Mars, how will this benefit us back on Earth?
Again, a question of high societal impact. Again, a question we discuss very often. So yes, I know how it might benefit each and every one of us separately. It might help us progress our way of thinking on life on Earth, understanding that, for example, if there is life elsewhere in the universe, if we're not alone, then we might change our even respect for life, for example, on Earth. There are other benefits that they might come up depending on the properties of the life we might find there. So I cannot know yet because we have not seen it yet. But one thing is certain, it will change our perspective of how we perceive life on Earth.
Okay, so
thank you very much.
Oh,
sorry to interrupt
lots
again.
of questions for that one.
Yeah, I think it's fascinating, and I guess there are some really important points you pointed towards, as well as the ethics. But I hope you'll take the time to answer some of those questions offline, and then we post them. Thank you. And with this, we're going to the next speaker, Rachel Hassler, a soil ecology PhD researcher at Cranfield University.
Hi, thanks for the intro. I'm Rachel. I work in the Environment and Agri-Food Department at Cranfield, and I study soil. And in particular, I study the microbes that we find in soil. So microbes are everywhere, but they're particularly abundant in soil. So I don't know, maybe you've heard this before. But in just 1 teaspoon of soil, there are more microbes than there are people on the planet. So that gives you hopefully a bit of an idea of just how abundant they are. And they complete some really important functions. They help provide nutrients for plants and trees and crop growth. They're really key in the carbon cycle, which is particularly relevant these days as we're seeing more of the impacts of climate change. And within the carbon cycle, they're really important for decomposition functions. So when we have something that's a really woody material, like this, there are particular fungal groups in the soil that help decompose this. And they can decompose the really woody and tough to decompose carbon forms like lignin and cellulose. And if they didn't do this, we'd be in trouble, because all of the woody material that ever existed would still exist, and we'd be up to our ears in it, and there wouldn't be room for us. Another really important thing that they do is provide nutrients for our plants and trees. So, for example, if you imagine that this is a tree root, and it's pretty thick and it's pretty good at getting through the soil and collecting the water and nutrients that it needs for its growth. But if you imagine this tree root, it can't get everywhere, and it can't get into the tiny spaces that exist within rock. And within rock, there's some really important nutrients like phosphorus or phosphate. And so our fungal helpers come in again, these microbial fungi that form things called hyphae. Now, these hyphae, they are thinner than tree roots or plant roots. They're quite similar really, but they're a lot smaller. And they form something called a symbiotic relationship with the plant or tree roots. And symbiotic means that both parties, the tree and the fungi, benefit. They both benefit from this relationship. So they form a relationship, they wrap around each other and within each other, and these fungal hyphae can get inside this rock and pretty much mine out phosphorus and pass it along the hyphae into the tree root. And this is just one reason why I think soil microbes are fascinating. There's a really important factor in soil, is that within this carbon cycle, within the terrestrial carbon cycle, soils hold up to 80% of all the carbon that's found in the terrestrial pool. That's something like 2,500 gigatons of carbon. And if we manage that, if we understand our relationship with these soil microbes and what we do, how it affects how they complete these functions, then we can better manage the carbon cycle, and we can benefit more from the effects of these microbes, from the functions that they complete. And that's where my research comes in. I'm really lucky to work with the RHS at their field trial in Wisley, where we add different carbon sources to the soil, different compost, different organic matter, and we see the effect. So if we add something that's really woody to the soil, what effect does this have on the fungi and on their buddies or their competitors, the bacterial population? And how can we better manage what we do to soil, the human land management aspect that affects the carbon cycle? And I'd just like to say thanks, Soapbox Science, for having us. What a fantastic platform for science communication.
Thank you very much. That was great. Great props. Any questions?
Let me just see what's come in. Okay, so the first one we have here is, what does your day look like? What's a typical day for you, Rachel?
Well, I think, yeah, it's really nice being a soil science researcher, because it's pretty much every day is different. Some days I'll be, like I say, at a field trial and I'm covered in mud out in the rain, which I love, you know, collecting soil samples, working with a team of people that are real horticultural experts at the RHS. And then the next day I'll be in the lab in really controlled conditions, working with amazing different chemicals to kind of find out what's going on in this unseen galaxy beneath our feet. So yeah, it can be really different every day. Obviously, I'm working at home at the moment, but no, it's really varied. Yeah.
Okay, so thank you. So we've got a question coming in from YouTube here. Can allergens like wheat or nuts live in the soil, and how can you manage this risk?
Well, I think if there was a field of wheat grown somewhere, then yeah, there would be remnants of that within the soil. But these microbes are working to decompose all the time, unless there's something really catastrophic that's happened in that field, then yeah, they'll be degrading these things and decomposing them. And if you imagine something like wheat straw, it's made of different forms of carbon, amongst other things, but microbes will be working to decompose this, yeah.
Okay, so we've got another question coming in from Facebook here. How does the use, I don't even know if I'm going to say this right, of fungicides impact the quality of soils?
Yeah, it's that's a big question and something I'm really interested in. I think not all fungi are beneficial, and there are fungi that can wipe out entire crops. So obviously fungicides have their place if it means ensuring that there's enough food for everyone. But, and there is a big but, we're finding out just the impact of using fungicide on things like soil fungus. So it can be a trade-off. In some areas, it could be a real benefit because you won't have a crop unless you use a fungicide.
Right.
And in other areas where they may be being used as a preventative measure and there wouldn't be a problem, if then perhaps it's unnecessary and having a detrimental impact on soil fungi that would otherwise be providing some really important benefits to crop growth. So yeah, I think it really depends on the individual circumstance.
Okay, thank you. Got one in from YouTube. What is the biggest threat to microbes in the soil?
The biggest threat. The biggest threat is probably people thinking they're boring. Because I really think, I mean, I loved Sebi's talk before mine. I mean, microbes are everywhere, and I don't think people really realise just how fascinating it is. It's like space exploration, yet it's just under the ground, under our feet here. So yeah, that's probably my best answer for that one.
Okay, we've got another one here. What's the difference between a mushroom and a fungi?
Yeah, so that's it. Yeah, that's a good one. The fungi is the whole organism, including the hyphae, the whole mycelium that's made up of hyphae, and the mushroom is the reproductive organ of the fungi.
Okay.
So it's the above ground kind of, it's not a flower, but if you imagine it's kind of the bit of the organism that is responsible for reproduction. Yeah.
Okay, thank you. So we've got one in from YouTube here. How do things like using fertilizers, especially overuse, affect the microbes?
Yeah, that's a good question. That's actually a big part of my research and something I'm quite interested in. I mean, again, fertilizers are really important for ensuring there's enough food for everyone, but there is often overuse of them. And if you over-fertilize, it sometimes means that these associations I was talking about between plants and fungi aren't necessary. They won't bother forming them. So we do have a big impact on the soil microbiome by adding a fertilizer. So it's really important to think about this. Do I actually need it? Can I provide it through other inputs that actually have a beneficial effect as well, like improving organic matter by adding composts? But yeah, fertilizers are also necessary in some situations. Again, it's really circumstance, but there's a lot of research going on in that area as well.
Okay, thank you. Have we got time for another question, Barbara?
Yeah, one more question.
Okay, this might be quite a big question
Uh-oh.
that's come in. Why is soil so important?
Oh, that's good. Soil, I think, is the overlooked natural resource. I think we take it for granted. I think we really think about water quality a lot because we can measure it really easily by how polluted it is. And we can do the same with air quality. We can measure how polluted it is quite easily now. It's quite an established way of doing things. But with soils, I think we take it for granted. But really, all of our food growing, I know there are systems that are really funky, like in Natalia's talk, we're talking about like underground growing systems that are all grown hydroponically and things like this, which are really cool, but we still mainly rely on soil for the production of our food. And it also has other benefits that we're now finding out more about, that it affects our own microbiome and our own link with the land. And then there's all the kind of culturally historic and historical important sites that, like mountains and things like that, which are all have an impact on our cultural well-being and our social well-being. So I think it's yeah, it's really integral to life on Earth.
Okay, thank you.
Yeah, that's a big topic, and I guess it will keep you in lots of research for the future, hopefully, and that's great. I mean, that's what you want, right?
Thanks. Bye.
All right, so let's move on to the next speaker, Dr. Edith Rogers, a materials physicist from Cranfield University.
Hello, good afternoon. My name is Dr. Rogers, Edith Rogers, sorry, and I work at Cranfield University on a different topic to the other speakers. I work as part of the project design better detectors of positron emission tomography, which is an imaging technique which is used in hospitals to detect cancer. So why then, as you can see, I'm not in a hospital. Why am I standing in front of this nice milling machine instead of in front of the nice big PET scanner? So first of all, better explain to you what PET is, positron emission tomography is. So positron emission tomography is also known as PET. So it's not for your animals, not for the cats, but it's for humans, basically. And it uses a radioactive tracer, which produces two gamma rays that move in opposite directions to each other. Now, a PET detector doesn't really work quite like a normal camera. Instead of having one sensor, we have a whole ring of them like this. Oh, straight. So when we have our gamma rays produced, it goes onto the, it hits our gamma rays. We have hits the detector, and we get a flash of light. Pop it off. On the two different opposite sides of our ring here. And we can, if we know the timing difference between our two events, then we can work out just how long where in this line the event happened. And the faster we can detect our light, the more accurately we can work out the timing difference, and the closer we can get to pinpointing the event, which means we can get a better picture faster. And this is what we call the timing resolution of our system. So at the moment, the best resolution we can get in a hospital machine is a few hundred picoseconds. So that's about a 10th of a billionth of a second. But what we really need are detectors with a timing resolution close to 10 picoseconds. So that's 100th of a billionth of a second. So a very, very short time period. But why do we even need good timing? Well, in order to accurately find a tumour in a cancer patient, we need to have enough information in order to reconstruct a picture. So if you've ever taken a photograph in the dark room and you've forgotten to put your flash on, or you've tried to take pictures of some fireworks on your phone and not read the settings in right, you know, you don't tend to see very much. You get a very grainy, very noisy picture. And this is because not enough light is reaching the sensors in your camera. And this is actually a very similar problem to what we can see in PET. If we don't have enough if we don't detect enough radiation and we don't get an accurate positioning, we can't make a good picture. And obviously, with things like treatment, like modern treatments such as proton therapy, you really need good positioning. You don't want to give a patient radiotherapy and put it 10 millimeters to the left of the tumour. That's really bad for them. So if we can sort of try and fix this, try and get better results. So one way we can do it is to give the patient a load of radiation. You can kind of see a problem with that. We really don't want to kill our patients. So what we really want to do, we could try to take a picture for longer too. You know, we could sit the patient there, stay still for a very long time. But even if we get someone to stand straight still, we all breathe, we all have hearts that are beating, and well, you move and you'll get a blurry picture. So then the thing we can do instead is make better sensors. So if we can get a better timing resolution, we can work out more accurately where between our two sensors, between our two detectors, the event happened, and the less radiation we need, the faster we can detect the image, built-up image. So what we really would love to do as well is have real-time imaging, and we can't do that right now. So what I work on is the detectors to try and improve this. So for our detector, we use a material called a scintillator. which converts gamma radiation, which is nasty to detect, into light, which is lots of sensors can see. You know, your phone camera can see it. The ideal PET insulator needs to be quite dense, so we need to capture gamma rays, and they've got loads and loads of energy, and they don't slow down very quickly easily. So we can be, we also need it to give out lots of light, so we can be more certain that our event is real, and we need it to be very, very fast in order to give us a good timing resolution. So at the moment we use single crystal. So this is a single crystal of, I think this one is LSO. They're very dense. They can be very bright, but they're never going to be fast. So here's another crystal. This gives you a bit of a scale. This is actually how big they are in a PET scanner. So this is 5 millimeters by 4 millimeters. So we've got a bit of a problem here. We're not fast enough. The other type of scintillator we use a lot is a plastic scintillator. So this is an acrylic, very similar to what you might have at home in your house for various bits and pieces. So it's a plastic scintillator. You can see if you put a UV light next to it, it glows. So they're very fast. They're very, very, very fast. They're more than fast of what we need, but they're not dense enough. You know, this is very light. So we need to look for a new kind of scintillator. One route we can take is to use something called quantum dots. So you might have seen those in the big expensive televisions in John Lewis. These are very, very, very small crystals. So one quantum dot is around 5 to 10 nanometers across. So you can fit around 10,000 of them across one strand of human hair. So they are very tiny. They are very, very bright emitters, so you get lots of light out of them, and they emit very quickly. And I have some here. So these are some quantum dots. I can pick them up in plastic. So if I put the detector next to you can see they glow really bright green. So these are quantum dots.
They look great.
Oh, I almost need to finish.
Yeah.
Okay, so they're not fast. Even still, they're not dense enough. So this is where the drill comes in. The drill allows us to combine two types of material. We can combine our crystal by machining it, and we can fill it with our plastic. And this means that we can use our big drill and our tiny materials in order to see light faster. Sorry about that.
No, that's great. I mean, it's fascinating, and it sounds like it's really important research, and as well as, you know, glowing things are always great. But we hope to have some time for you to answer some questions.
Okay.
Okay, so first question that we have for you is, how long does it take to develop a new medical technology like this? You know, how long are we thinking? Is it months or years, decades?
Years to decades. So if you look at the hospital stuff we detect at the moment, the current top of the range technology would be LSO, which is this stuff. The hospitals in the UK still use BGO, which is this stuff, which is 20 years old. So within 10 years, we should be able to go for, you usually tend to go, is about what you expect to get from the first principles for a project, but it will take longer still for it to get into hospitals. It all depends a lot on the cost and the ease of manufacturing.
Okay. So another question that we have here is, why is that drill so enormous when you're using such tiny things?
So this is a precision drill. So the enormousness of it is so that we have very good control of the X, Y, and Z direction. So we can direct this drill to within half a micron in some directions and a micron in the others. So okay. we can do very, very precise work.
Okay. Let me have a look. I think there's possibly there's one just come in from YouTube. Great to see your fancy machine, Edith. What other applications can use the detectors that you're working on? And that's come from Stacey.
Okay, so there's the obvious stuff. Anything that detects nuclear radiation, gamma rays is using nuclear. There's also some slightly more weird ones you might not realize. You can use it to detect, you can use sort of scintillators in general to detect things like damage in buildings. They use it a lot for mine detection. That can be used anywhere where you want to see inside things. There's a lot of X-ray detection. So there's hospital X-ray. There's also, so you've got a beam in a piece of construction work and you want to see any weaknesses, you can use X-rays and gamma rays for that. So, and also in a completely scientific way, a lot of the work we do, a lot of medical imaging work is done in CERN, because in order to detect all these fancy Higgs bosons and the rest, you need to have really, really good detectors. And scintillator detectors are very good for that.
Okay, thank you. We've got a question coming from our Facebook feed here. When this is developed, what is the goal size of the cancer to be detected? So how big a cancer would it be able to detect?
I don't know, actually. I'm a material physicist rather than a medical physicist. I'd have to ask. If I ask, I'll put it up on the Facebook. But I can't remember the resolution. The resolution depends on a lot more than just the crystals. It depends on the arrangement of the cameras and everything else.
That's okay, thank you.
Great, thank you. Maybe you can, sorry to interrupt again. Maybe you can, you can find that out from your colleagues and then answer that and post it. Thank you very much. I'm sorry to cut the time short.
No worries.
We have now our final speaker, Dr. Zhao Zhao Sun, a gas turbine combustion scientist from Cranfield University.
Hello, I'm Zhao Zhao Sun. I'm a research fellow in gas turbine combustion at Cranfield University. So speaking of gas turbines, usually there are two main applications. One is for land-based power generation, so it's sometimes connected to the grid. And so it produces a large amount of energy, and it will be used by everyone, not only in factories, but also at home. And the other application, important application, is to use gas turbine serve as an aero engine for propulsion. So basically, in terms of working principles, the gas turbines converts energy to work power or thrust, in particular for an aeroplane. And in order to have energy, you must have something that you need to burn. You need to have fuel. So it's important that people focus research on fuel and combustion, because it can bring a lot of problems, but it's also solving a lot of problems in terms of producing energy. And I'm not going to show you what an engine looks like because it's too big, but I can show you how combustors in engines look like. For example, this is about a quarter of a combustor in an aero engine, a medium or small size aero engine. And it's basically a ring. And there are many holes for combustion's purpose for fuel and air to be mixed. And there is another one that is from a famous engine, RB211, which is by Rolls-Royce, and it's used for many years to power the Boeing 747. So this is only a sector of it. You'd expect there are 20 to 30 of the same thing in a ring. And in this combustor, or many combustors, the most important part is a fuel injector. So this small piece, basically, it's in charge of mixing fuel and air in different ways and with a lot of sort of aerodynamic features. And our purpose is to give you the combustor a very homogeneous mixing. That means that the fuel and air is the same everywhere, but it's just ideally. So a lot of technologies has been used or researched to promote that homogeneous mixing. And you can see that in this type of combustors, basically the flame will sit in this region. So it's the size of my fist or a bit bigger. And traditionally, people have been using so many years hydrocarbon fuels. And the problem with hydrocarbon fuels, such as kerosene or diesel or natural gas, is that you produce emissions, a large amount of emissions. And global warming has been a huge issue for many years. And it produces a large amount of CO2. And that's not good for people. And it also produces nitrogen oxides. That means nitric oxide or nitrogen dioxide. And nitrogen oxides is also a global sort of greenhouse effect gas, but also it helps actually the ozone to deplete. That is not good in terms of global warming. And it also will, if people breathe in nitrogen oxides, there will be respiratory symptoms. So it's not good for human health as well. So the main thing to control that in a gas turbine or aero engine combustor is to control the production of CO2 and NOx. And well, you might say that what about reducing the number of flights or reducing gas turbines so that like reducing number of vehicles and limit this? Of course, this is a solution, but it's reported that the demand of air travel is going to grow in next 20 years by 4% every year. And since the pandemic, it's been declined by 50% this year. But you cannot rely on this type of thing to control your air travel limit. So it's really necessary to develop sort of alternative solutions to reduce emissions. And the most important thing is, from a fuel point of view, if you use a cleaner fuel, then that will be better. So my focus is mainly on hydrogen, and it is a fuel that if you burn it, the only it only produces a large amount of water. So there is no carbon emissions. And it's also very energy efficient. If you bring same amount of hydrogen, and currently we're using kerosene, it will produce 2 or 3 times of energy. And so this is a very attractive fuel for everyone to use. And there are a lot of perceptions and that people think that using hydrogen is not safe. So our project is to show that, Enable H2 project that I work on is to show that we can use hydrogen safely as a combustion fuel for aero engines that people can just fly in the future with an aircraft, maybe in year 2035, as Airbus announced, or in year 2050. And that's basically it.
Great, thank you, Jojo. That is really fascinating, and I'm sure people have some questions about that.
Yes, they're coming through. So first ones come from Facebook, from Sarath. Do you think fuels other than hydrogen, such as clean burning alkanes or alcohols and ethers, have scope in the future for the aviation industry, given the long time to implement hydrogen?
Yes, it is. It will be a long time to implement hydrogen, and we need sort of intermediate solutions. Some of these fuels, like alkane or alcohol, the problem is that there is not a lot of application going on burning these fuels. If you consider it as an intermediate solution, it also needs development from very low technology readiness levels. And in the industry, people are more lean onto things that they already used if you want an intermediate solution. And for example, natural gas, people will consider maybe, because it's being used in land-based gas turbines, maybe they can be used in aero engines because it produces less CO2. But still, we have to remember all these hydrocarbon fuels, they still produce CO2. But if we want to reduce CO2 by a large amount, then we need to have a better fuel like hydrogen.
Okay, thank you. So someone else has asked, what material is the combustor that you held up made of? They've said it looks really lightweight.
It's not actually light, but it's made by nickel alloy, for example. And this type of alloy can usually sort of sustain temperature about, let's say, above 1,000 Celsius degrees. And it's mainly sort of aerospace material. It's not very light, but it's I'd say it's not very heavy. Consider how big the engine is.
Okay, thank you. Another one come through from Facebook. How do you store the hydrogen in a plane?
That's a very good question. Here in Enable H2, many people think that because hydrogen has a very low density, which means for the same amount of mass, it's going to occupy a large volume if it's gaseous. So we are going to use liquefied hydrogen. That means to store it at a very low temperature. It's minus 200 Celsius degrees. So it's liquefied. And it's just like the liquid kerosene that we're using. But we will need more process about it to convert this liquefied cryogenic hydrogen to a gaseous fuel. So that is part of this Enable H2's scope to work on technologies to allow that to happen.
Okay, thank you. So we've got a question from Catherine from YouTube. Are there any experimental planes that are already running on hydrogen?
Yes, we are doing experiments here. For example, this is what we want the injectors to look at compared to the conventional ones. So there are many small injectors, and we are looking at, combine 3D printing technologies to these very, very small injectors and to see what the flame looks like. So I said that the flame was going to look like my fist in a conventional combustor, but this one is going to be much smaller for hydrogen.
Okay. Thank you. Another one from YouTube. How will the materials in these engines be affected by the large amount of water being produced?
It's going to be in vapor state because of the high temperature. So within the whole gas turbine, the production of water is going to be in the vapor state. It's still gaseous. And yes, the material may need to be changed and or to improve to prevent the effect of water. But for example, gas turbines in land-based, they already use something called wet low emission. That means using water to reduce temperature, to reduce emission. So it's already something we are considering. It's not to be going to be a huge challenge. But for hydrogen, we might face a challenge that if there is a hydrogen leakage, for example, then we have to deal with material problems.
Okay, thank you. And I think we've probably got time for perhaps a really quick one. No?
Yeah, really quick one. Really quick one.
It's a good one. If we can harness hydrogen and develop the tech, will my holiday abroad be cheaper in the future?
Well, probably we are going through a phase that the ticket will be, price will be increased to promote this technology that people want such an abrupt change, and then it will go down. I think in the long term, if we use renewable ways to produce hydrogen, it's certainly going to be very competitive compared to current technologies.
Okay, thank you.
Great, thank you very much. As always, time flies by during Soapbox Science events, and we are at the end of our first Soapbox Science session today. And I know there have been more questions and could have been answered, and there's so much more fascinating things to talk about from our speakers. But in order to to keep it to a reasonable time format, I think we have to stop it here. But I encourage everyone to go to YouTube and go to the individual introduction videos and post your questions there and have a discussion. And I ask the speakers to check that and maybe answer some there, so that we can keep the conversation going there and find out about all of this great work they're doing. And with this, I'd like to thank our speakers for their amazing presentations and all of the people who joined us today to listen to the talks as well as ask questions. Thank you very much. And it's great that we could have had an event in this format. I'd also like to thank my fellow committee members from the organization of Soapbox Science Milton Keynes for all of their great work leading up to this event, as well as making sure that everything runs very smoothly behind the scenes today. And a very special big thank you also to AJ, Sam, Katrina, and Ben from the Open University for their know-how and technical support to have this live broadcast of our event today. I'd also like to invite you to join us for our second part of the Soapbox Science event this Saturday, again at 2 p.m. On YouTube and Facebook. So make sure to come along to that too. And with that, goodbye for now, and I hope to see you on Saturday again.